Alright, so type of discontinuity, first thing we see we need to factor. I gave you kind of an easy one for a warm-up, and it was in your packet. So we have a hole at x equals 4, and remember it's removable. If you graph this, what would it look like? It wouldn't be continuous because we have a hole. What would it look like though? What shape would it be? So look at this. Those cancel, and so what you're really graphing is this. What is that shape? That's a line with a slope of 1, except for we will have a hole where x equals 4. Otherwise it's just a line. So it's going to look something like that going through where the hole is at x equals 4. So is that continuous? No. Okay. And so, oh, why did you say it? Yeah. So I think Judd has a question about the homework, and anybody else if you have any.
Okay, can we go over 6?
6, sure. Alright, so again, I gotta remind myself the directions. So type of discontinuity and where. So remember with trig, we need to rewrite so that it has, so we can see a denominator. And then even from there, it's more work because we have to find all the places where the denominator is 0. So what is secant when we write it with the denominator?
1 over cosine. 2x.
And we want 2x still there. Okay, so fortunately or unfortunately, it's the same kind of process as what we did in the example problem, where we need to find where cosine 2x equals pi over 2, 3 pi over 2. Now that takes us around the circle once, but because of the 2, we're going to have to go, we have to keep checking. Let's say it that way. So remember the next round, and I kind of sketched this yesterday. So pi over 2, 3 pi over 2. To get from here back to there, because we're going around again, is another pi, right? Or from here, 4 pi over 2. So our next one is 5 pi over 2. In other words, pi over 2 plus 4 pi over 2. 4 over 2 is just 2 pi. So a whole revolution around. Okay, now we'll do the same thing here. To get from here all the way back again,
7
is 3 pi over 2 plus 4 pi over 2. So that gives us 7 pi over 2. Okay. Now, because we did this yesterday, we know that's far enough. But if we were doing something else, like a more complicated trig function, you might want to check that you don't need to keep going around, right? Or like if this was secant of 4x, we would have to keep going to get all of the places where it's equal to 0. And then we're solving this. Where does 2x equal pi over 2? Well, if we divide by 2, x becomes pi over 4. And that's going to happen on all of these. So it's just going to be repeated, but with 4's in the bottom. So if you plug in pi over 4 here, you get pi over 2. Cosine of that is 0. So we have a vertical asymptote. Yesterday, I think we didn't say what kind it was. So this is where it happens, and these are all vertical asymptotes. In fact, I'm going to go see that. Pretty sure in the example problem I forgot to write what kind it is. Yeah, so I'll put it there just in case you go back and look today. Did that help, Judd?
Yep.
Okay, any others that you'd like to go over? And you're checking so you know they're going well, everybody?
Yes.
How about the test prep? Do you find those helpful?
Very.
I like them. I think they're good.
I like the more than non.
Yeah. Alright, well, if there are no other questions, let's get into the next section. So 1.11. Actually, I'm just going to leave that up like that so I don't have to do it twice. So, defining continuity at a point. Here's where we take the lower classes definition of continuity where, oh, I don't have to lift my pencil, and we formalize it to an actual mathematical definition. So from this point on, now we need to use this definition to define continuity, okay? And you'll see some justification steps that you have to do. I think I'm going to come back to these after we do some. So let's do, oh, I skipped it. Uh-oh. I don't have it. Hold on. Let me get this. Alright, so here's our formal definition of continuity. You notice it has... Alright, 3 criteria. All 3 must be true. Must be met or true to be continuous. So before we do this, I bet you can come up with them, perhaps, or at least a couple of them. Knowing that we informally say that the graph, you can draw it without lifting your pencil, in calculus wording, what do you think that means? And think of the stuff we've been studying.
F of x must have no holes.
Okay, so we can't have a hole.
Or
That's true.
asymptotes.
Or asymptotes.
Or discontinuity.
Or what's the other one? Or
Jumps.
jumps, right? Okay, well that's good. Which means what about the limit? Like basically what you all said.
Must be
for the most part. What has to be true about the limit?
It must go from, wait, no, never mind.
Every point on the line must have a definable limit.
Okay, so it has to have a limit, right? Okay. If you want, you can draw this. And I'm just making one up. Let's say we have some curvy function. And there's a question here about what's going to happen. And then it keeps curving off. So, what has to be true in there for this to be continuous? Somebody, well, writer said, can I have that hole there? No. How do I plug that hole? In function and calculus wording. Let's call this function f. Well, first of all, do we agree the limit has to exist? We said that, so it has to come into the same point from both sides. But what about that hole? How do we describe it in calculus language that can't be there? Using the function name. Right now, does that point exist? No. So it has to exist, right? And it has to be, the function's value has to be that same as that hole right there, okay? So here are your 3 criteria. We're going to use C for the point where we're analyzing continuity. So some random x value C. So for f of x to be continuous at that point, at x equals C, f of C must exist, which means C must be in the domain of f. Do you guys remember yesterday we would have like a function like this and we said, hey, it's continuous on its domain because that point isn't in its domain. That was kind of confusing. So C must be in the domain. Okay, number 2. The limit, let's just write that instead of all the words. So the limit as x approaches c must exist. That hopefully, like, in your mind, hopefully that kicks out the two-sided, like, jumps, right, when we have different one-sided limits. Okay. So these two are true, but what keeps it from being this case? How do we describe changing that's not a jump. How do we describe it in this last criteria to say that existing point has to be in there?
Say it out loud.
You can get on Trevor's phone and call me if you need to.
I have it right.
I'm just kidding. Yeah, go ahead and say.
Hey, you just whispered it to me. It sounded
Yeah.
familiar. I don't know.
Right, well, here's what we'll say. That last criteria says the limit as x approaches c has to equal f of c. Okay? So the limit, like whatever limiting value this is coming into, has to be equal to the function's value at that point, and now we plug that hole. Okay? So these three criteria have to be true every time for continuity to exist. Alright, examples. State whether, anytime you hear state, we're going to probably have to tell why, right? Well, sometimes. Alright, what kind of function is this? What do we call those?
Piecewise.
That is piecewise. So we're stating whether or not the function is continuous, first of all, at x equals 1. So we need to analyze those three different criteria. First thing we need to analyze is the limit as x approaches -1 from the left. Since this is a piecewise function, if you start thinking graphically, I want you to think of it like this. Let's say it does something like that. Obviously that doesn't meet the criteria, right? Like this is a piecewise function, but the limit doesn't exist, so it won't work. But we could also have a piecewise function that does something like that, where we have a horizontal and then a slanted line, or maybe then a parabola. Right? So just kind of think in your mind what piecewise looks like, or can look like. So we are checking left and then right. Why are we checking left and then right limits?
So you could,
Determine it's continuous.
What are we looking for in our investigation?
Make sure they have
The same value.
Yeah, if they have the same value, we know the limit exists. Okay? So let's do that. So from the left, this has no indeterminate form or any funny business, so just plug it in. So 1 plus 2 plus 1 is 4. Okay, now we'll do the right-sided limit. Okay, so those don't agree. Which means what?
it's not.
There's no limit, right? It's not continuous. So the limit as x approaches -1 does not exist. So f of x is not continuous at x equals -1. Alright, next one. Do you want to try that one?
Yes.
Cool. Try the x equals. Alright, so that's good, these agree. So we have criteria number 1 met, right? Which is the fact that the limit exists. So we can say, well, I'll say that in a second. Alright, how do we check the other 2? Criteria, I mean.
Plug in somewhere to prove that.
Okay, now we need f of 2, right? So we need to see if f of 2 exists. So f of 2 equals what? How do we read this piecewise? It's where it says or equal to, right? Is 2 to the x or 2 to the 2, so forth.
How does that check?
So yes, f of x. Now, you guys remember early on in this course I told you to use NUT, name, unit, time, when you're analyzing? So name, I just wrote f of x. Unit is irrelevant in this one because we don't have any. But the time is where this occurs. So yes, f of x is continuous. What? What comes next? At x equals 2 because the limit as x approaches 2 equals 4, which equals f of 2. So we are good. Okay? Are we good?
Yes.
Okay. How'd you do? I guess I should ask that. How is your description? Did it meet the criteria? Alright, this one's kind of interesting. This looks like a carryover from yesterday. So identify the type of discontinuities that occur and where. So how do we know if there's a discontinuity?
If one of the rules doesn't.
Yeah, if those 3 criteria fail somewhere, okay? So let's check the limit, the left and right limits. So 4 from the left. And then 4 from the right. Okay, so what kind of discontinuity does that look like? We're coming into the left of 4 at 13, and we're leaving or coming into the right of 4 at 1. So what do we call that?
Jump.
That's a jump, right? Now, if you noticed on your work yesterday, you only had asymptotes or holes. You didn't have these. So now you kind of know how to look for them. Okay, why don't you try number 3? Alright. Huh?
That's the main thing.
Yeah, that's pretty awesome. Alright, so nothing, like when we're looking at these, we kind of have to use the intervals on the right to tell us even where to look. Hopefully that's clear. So the limit as x approaches -1 from the left. We're going to use that function. Did we already do that one?
No. It's different.
It's slightly different.
Yeah. It's like this right.
Yeah, because that was a negative, I think.
Oh, I got it.
Alright, so 1 minus 2 is -1, minus 1 is -2. And then we'll use x minus 1. Alright, so it's looking good so far. What has to be true though? So think about like this is coming in at a parabola and then it's leaving as a line. What's going on right there? So f of -1 is what?
5.
It's 5, not -2. So it's like this. And what do we write there? Okay, so we have a hole at x equals -1. How'd you do on that one? Alright, last one. We'll do more of this, but actually I say last one. It's the last one on your paper. I'll probably show you another one here of those slides I skipped. So this is we're gonna have a section called removing discontinuities, but this kind of introduces that a little bit. So it says let h be the function defined by this piecewise. What value of k would make h continuous? So that k right there, notice, is part of one of the function rules or pieces. Any thoughts? I mean, it has infinite possibilities right now. How do we figure out what to use to plug that hole?
Can we just set them equal to each other?
Hold on. Ocean, can you, for a second, so I can hear Mr. Pedro?
Can you just set them equal to each other?
Set what equal to each other?
The two functions, so that
Okay, so he's saying, let's set these two pieces equal to each other, and then solve for k. What do we plug in for x?
-2.
Yeah. Okay. So let's kind of give some background. To be continuous at x equals -2, the function value must be the same there. Okay, so that's the theory or concept behind it, which means we just set 2 minus x squared equal to 4x plus k, and then we can plug into the x, not to the k. We can plug in the -2, so 2 minus -2 squared. Okay, so 2, what is this? 4, 2 minus 4 is -2. Don't you like it when you're in calculus doing algebra 1?
Yeah.
That's nice, right?
Yeah.
Yeah.
Yeah, -6.
So if k is 6, we have now plugged that hole and there's no discontinuity. So that's kind of nice. We'll do more with this, like I said. In fact, let's do another one. Sorry. Starting to be choked. Alright. I'll just give you a minute or two to work on. Yeah, let's see if I can move some stuff around.
Let's go.
Okay, don't forget that this one can GCF factor. Once we've done that, those cancel. Okay, so this is really, like, think about the fact that in this case, if we plug in at the point in question, this one would be indeterminate. So we have to manipulate that a little bit first. Otherwise, if you just set these two equal and you plug in 3, what's going to happen? Nope. Nope. Okay, so here's what I'm saying. If we just set these equal, like in our note just a second ago, we said, hey, just set them equal. But if I just set those equal, 3 squared minus 3 times 3, I'm going to get this. And is that, do I just stop there and say, well, there's no value of k? No, so we have to manipulate the equation, the first piece, so that we can solve for k. Because now we're good. So we just plug in 3, so 3 minus 3 over 3, that's 0. Okay? Yes?
X plus 30.
X, yeah, you're right. I got a little wild with my scratch off. Sorry.
It's okay.
Good job. I like to see hands come up when I mess up. I don't like to mess up, but I do. Glad you guys catch it. C? Okay. Can anybody graph it?
Yes.
I want to see us graph that on the Nullmarks calculator.
I literally have the phone in everything.
The sun's coming out and it's still raining. Is there a rainbow out there?
I don't know, I can't see.
Ocean, look for me.
Okay. Or you could be graphing this instead.
Yeah, we can graph this instead.
And practice using your fancy calculator.
Oh my god, it's dead. I don't believe this one is dead.
Okay, so there's that point in question, and so look, I'm gonna do it from up here so you can see me. This is a cool thing on this calculator. Everybody listen up. So if you click over to the 3 dots on the right, there we go. Later on we'll do derivatives. That's a calculus thing that we do next unit. You can change the color, but we can also do a plot restriction right now and say that this is for x not equal to 3. So we might have to enter it twice, but so x min, let's, I don't want auto. Yeah, I don't think so, you're right. Never mind. This isn't what I was thinking it was. Oh well, we can see what the graph looks like at least.
It'd be best for like piecewise.
Yeah, we'd have to put it in as a piecewise. I'll look into that. Alright. On your packet, you're going to do the evens and the test prep again tonight. It's the same kind of idea. So if you have time to do it before we're done, like 4 minutes if you want to start. And remember, I don't see you guys till Thursday. So in between, if you need to come Coming from the left, then we just drop that absolute value. So it'd be like negative.
The first time I bet on Dragon, he took me through a roundabout. In his school, that one said.
No. Now you, because you dropped the absolute value.
The roundabout.
You're just left with
Driving all over.
well, I do like the way that
I drove from the credit in that year. My dad. Like, you got mad at me. You left them on, like, you clearly.
all you're left with is.
Yeah, it's my fault.
And if it's coming from the right, you just drop the absolute value. See you guys.
No way.
One is so you would rewrite it as 1 over sine. Oh, you did. Okay, so if we need, so in order to find the vertical asymptotes, we need to find where sine of x over 2 is 0. That's where sine is 0.
So then, sine
Okay, but so yes, pi and 2 pi is where sine equation is. But we might have to keep going around to get all the way through our interval of 2 pi. Okay, so we might. So basically, like, evaluate at pi, 2 pi, 3 pi, 4 pi would be my.
So I
That's
get
how I would start.
pi over half.
No.
No.
Yeah, don't do that yet. Just say, like,
So
sine is 0 at pi,
Pi.
2 pi, 3 pi, 4 pi. And then let's just stop there and see how far that takes us. So now, that has to be what is inside of the sine. But right now it says x over 2. So you just set x over 2 equal to each of those and solve.
And then the answer is just 1 over whatever 1 is.
Go plug it in, like x over 2 equals pi.
So, pi over sine of half pi is.
Okay, no, you're trying to overthink this. Do you agree that for this to be 0, x over 2 has to be pi?
So it would
Right.
be 2
So
pi over 2.
set x over 2 equal to pi. Right there. And that's all that is.
So
Right, x equals 2 pi. No, because
They change.
it's only it's only up to 2 pi, and so you're already there. So that's it. You need more. If this had been like 4x instead, we'd have to cycle around. Do you remember from pre-calc changing the period?
It's like one of the last things we did.
Yeah. That's essentially what this is. So that in that case, it only goes to 2 pi. It doesn't keep going around.
I forgot everything from pre-calc the second I left the test.
Well, hopefully this will remind you.
Students, a reminder, softball has been canceled
Thank you.
and tennis
Yep,
is canceled,
see
so
you.
no one is leaving early for those sports. And I have not heard yet for soccer. So soccer is still on as far as I know. Thank you.
See you right in.
See you.
What did you say, Caleb?
Did I miss anything yesterday?
Well, what do you think?
I think I did.
Did you get on Google Classroom to check?
Yeah, it said no missing assignments or no assignments.